Hello and welcome to the Biomedisa YouTube channel. Segmentation of individual particles or cells is important in many areas of biology and geology. In this tutorial I will show you how to use Biomedisa to separate individual rock particles, sediments and mitochondria from micro-CT and electron microscopy images. We'll go through three different ways of working with Biomedisa. First, the 3D slicer extension, second, Biomedisa's online version, and third, the command line interface. All the files I use in this video, including the trained model, are linked in the description below. There's also a link to the paper that describes the method in more detail. The examples in this video are run on Biomedisa installations at the Pawsey Supercomputing Centre in Perth, which you can see here, which is a Windows environment, and later in the video also on the Gadi supercomputer at NCI in Canberra. If you are a Gadi user, feel free to reach out. I'm happy to share the Biomedisa environment with you. We start by opening 3D Slicer and loading our first example, the large particle dataset, using drag and drop. Next we go to the segmentation editor, add a new segment and open the thresholding module. We create a binary segmentation by setting the threshold to 12,000 and clicking apply. We then switch to the Biomedisa prediction module and load the pre-trained model from the paper. In the advanced settings, we increase the batch size from the default 12 to 512 and click Initialize. After the process finishes, you can scroll through the slices to inspect the segmented particles. If you are satisfied, click Apply. You can also visualize the result in 3D by enabling the Show 3D option. Next, we perform the same workflow using the command line. We open a terminal, for example by searching Anaconda prompt, activate the Biomedisa environment, and run the following command. Here the first two arguments are the path to your image data and the path to your pre-trained model. -m specifies the path to your mask. Here the mask must be created beforehand in 3D Slicer, and we use a batch size of 512 and save the result as an NRD file. This process takes about 18 minutes on the single GPU. Now we can return to 3D Slicer, import both the original volume and the result, and view the segmentation. We can also perform the same task using Biomedisa Online, upload the image volume, the mask as a label file and the pre-trained model, use the 2D preview to verify the setup, then go to the settings and again set the batch size to 512. Select the image volume, model and mask and click Predict. Once complete, you can inspect the segmented particles and preview the separated objects. Next, we repeat the workflow with a new dataset and using a pre-trained segment anything model. Create a mask using thresholding, this time with a value of 21,000, and apply. In the prediction module, we could again either reuse the previous model or show all files and choose a pre-trained segment anything model. Both Biomedisa specific models and general SAM segment anything models work well. The former are specialized, while SAM is useful for new or unfamiliar datasets. The same workflow can also be performed online. Upload the volume, the mask, and either a SAM model or a task-specific Biomedisa model and run the prediction. Next, we demonstrate a more complex example using an electron microscopy dataset of mitochondria. In this case, simple thresholding is not sufficient to separate the structures from the background. Instead, we use a pre-trained Biomedisa model to generate a binary mask. Because the dataset is very large, we first define a region of interest to speed up the process. After generating the mask, we apply a second model trained specifically for instance separation of mitochondria. And the result is a segmentation where each mitochondrion is separated individually. This workflow can also be executed online by uploading the image volume and the two required models, one for mask generation and one for instance separation. First, run the mask model. Then use the output together with the original volume as input for the separation model. Finally, we demonstrate the workflow on a multi-GPU system at the NCI Supercomputer. Gadi uses a Linux-based environment, and you can either choose up to 4 NVIDIA V100 or 4 H200. After opening 3D Slicer, we load a medium-sized particle dataset and create a binary mask using thresholding. In the prediction module, we select the pre-trained model, set the number of GPUs, which are here 4 devices, and again increase the batch size to 512. The workflow remains basically the same, only the number of GPUs has changed. The command line equivalent stays the same, but uses MPI by adding MPI run minus NP and then the number of GPUs, here 4, at the front of the command. As before, you first generate the mask, if not already available, and then run the separation step. The order of command line arguments is flexible, and for large data sets such as here with 1000 slices of more than 4000 times 4000 pixel, this can still be computationally intensive. For example, here around 44 minutes on 4 GPUs. Finally, you can visualize the results again in 3D Slicer by loading both the image data and the segmentation for further analysis and processing. Thank you for watching. Feel free to leave a comment below if you have any questions, and I'll see you next time.